Good morning, student. In this lecture, we will understand that how to start, stop, and reverse power flow is achieved in the HVDC system. So that is a starting, stopping, and power flow reversal in the HVDC system. So first we start the normal starting sequence of the HVDC system. So how to start the HVDC system? If it is already closed or if it is start from the starting, what is the procedure to start the HVDC system? So either the inverter or rectifier may start first. So that is the first step. You first start either rectifier or inverter. And the converter that is started first that establishes the valve firing and conduction. And the voltage is held low with the deblocking firing angle being between the range of 60 to 70. It means initially when you start any converter, maybe either rectifier or inverter, initially maintain the low voltage by the firing angle in the range of 60 to 70 degree. Then after following a communication delay, the other converter also establish the firing angle and that also maintain the low voltage with the firing between 60 to 70 and the starting current of the system is maintained of the order of 0.2 to 0.3 per units. So that is the second steps. Second step, you start the next converters with the same firing angle and maintain the voltage level. Another that the successful start has been established. After that, the voltage has been increased according to the relaxation rate on the firing angle. So the initial current order we have selected 0.2 to 0.3 per unit, that is maintained until the voltage has reached to the set point 40 to 80%. So once the voltage is reached to the 40 to 80% of the rated value, up to this point you maintain the initial current order 0.2 to 0.3 per units. After that you change the current order as per the requirement, you maintain it. That is the third step. And fourth step is when the current is established as per the required value or desired value, then maintained by the rectifier and inverter goes into the voltage or margin angle control modes. So again repeat this 4 point. When the current is established, whatever the desired order you provided in the third step, when this current order is established and that is maintained by the rectifier, the inverter is goes into the voltage and margin angle control modes. So that is the 4 steps to start the any HVDC system. So is this entire procedure that takes a short a time as a fraction of second or as long as several minutes. So that is depending upon the power order and limitation imposed by the AC system. So depending upon the requirements, the starting of the HVDC system takes several seconds to few minutes or several minutes. So the load may be increased exponentially or in small steps. So if load may be increased exponentially or in small steps, then as per the requirements, you start your HVDC systems. So this is the normal starting sequence of the HVDC system. Again repeated, first you start the any of the converter, maybe inverter or rectifier, and start with the firing angle such a way that the voltage had low and that is the range of firing angle is between 60 to 70 degree. Then after following a communication delay, because one converter starts, so that sends the communication signal to the another converter to start. So with this communication delay, the another converter establishes the firing angle and that also maintain the low voltage and with the firing angle again 60 to 70 and maintain the starting current on the order of 0.2 to 0.3 per unit. Third point, after successful start has been established, the voltage is increased according to the relaxation rate. So how to increase the voltage? As we know that by decreasing the firing angle alpha or beta, we can increase the voltage. So voltage is increased according to the relaxation rate on firing angle. Relaxation rate means decrease the firing angle and the initial current order of 0.2 to 0.3 is maintained until the voltage has reached to the set point 40 to 80% of the rated values. Clear? Then after the current order is released by the control circuits to the desired value, then fourth point is that when this desired current order is established and it is maintained by the rectifier at the DC side, then after the inverter goes into the voltage angle control modes or margin angle control modes. It means the inverter act as a voltage control mode and rectifier is act as a current control mode. That is a normal operation of the HVDC system. As you see in the characteristic, that also in the normal mode, rectifier operate in constant current mode or current order mode, and inverter that operate in the voltage control mode. So this is the normal starting sequence of the HVDC system. Next is the normal stopping or blocking sequence. So how to block the HVDC system. So as we know that in the AC system, we use a circuit breaker to isolate the AC line. Here, same way here, the DC link is shut down gradually by the controls. So the blocking of the pole is achieved here by reducing the voltage and current to the zero. So as we know that here, the DC line that is blocked by blocking the bridge. So how to block the bridge or how to open this bridge? So obviously that is by opening of all these valves in the bridge. So how to open this valve in the bridge? So that is by removing all the positive gate pulses of the valve, we can open this whole valve. So there are two ways you can open or stop this HVDC system. So one way is this one, that is called as a bypass valve with bypass switch operation, and another that is called as the bypass pair operation. So the valve blocking here is achieved by interruption of all the positive gate pulses provided to this all the valves in the bridge. And why we require this bypass switch and bypass valve here? So as we know that when you suddenly remove all the positive gate pulses of all the valves, that results in over voltage is created because of suddenly current extinction. So in some instances, the blocking of the valve at the inverter side generally, that creates the continuous conduction through the previously conducting phase and placing the AC voltage on the DC side and the direct current on the converter transformer. So because of that, to protect against this high voltage, we require the bypass valve as well as bypass switch. So therefore it is necessary here to bypass the bridge when the valves are blocked. So whenever we require the stopping of the bridge or valve, at that time we provide this bypass valve at parallel of this bridge. So this bypass valve bypass this bridge, and whatever the over voltage is created, that will not harmful hit the DC side and it bypass this bridge very effectively. So here we have two way to block this HVDC system. One way is by this figure number 1, this one, and another way that is this one. So here you use the bypass valve as well as bypass switch. So whenever we require the stopping of the HVDC system, remove all the gate pulses of this switch. At that time, provide the gate pulses to this bypass valve so that your current from the bridge transfer to this bypass valve. So current is flowing from supply to bypass valve and the DC side. So there is no over voltage is created at the DC side. After that, to remove the gate pulse of the bypass valve and close this bypass switch, so the current is transferred from bypass valve to the bypass switch. Clear? So again there is no over voltage is created. So valve current is now commutated from bypass valve and then to the bypass switch, and that is closed, so that relieve the bypass valve from carrying this continuous current flowing through the bypass valve. Clear? So here we provide the two switches, one is valve as well as bypass switch, but here that is provide only bypass switch. So that is another configuration you can use. Suppose the thyristor is used as a switch or thyristor is used as a valve per bridge. So instead of using the bypass valve, we require the only bypass switch. So when you close the bypass switch, all the current is transferred to the bypass switch. So that also not create any over voltages. So there are two ways to block this HVDC system. Next is the power reversal in the HVDC system. So how to achieve the power reversal? So all the HVDC systems generally inherent capable of power flow in either direction, from converter 1 to converter 2 or converter 2 to converter 1. So most of the schemes of the HVDC system that are fully controlled features and that permit the bidirectional power flow. So to get the power reversal smoothly, the following sequence we have to follow so that we can achieve the smooth reversal of the power flow in the HVDC system. So first step is that the reduction of the current to 0.1 to 0.5 per unit via the step and ramp. So here I'm talking about the DC current. So for when you want to reverse the power, at that time first you reduce the DC current to 0.1 to 0.5 per unit via the steps and ramps by the controls or current order signals. Then after decrease or increase the voltage via the ramp or exponential fraction followed by the current ramp to reach the required level. So as we know that the current at the DC side that ramp is positive, we achieve the reversal of power flow by changing the polarity of the voltage at the DC side. So suppose at the rectifier we have positive voltage, positive current, so current is flowing from rectifier to inverter. So rectifier is converter 1 and inverter is suppose at the converter 2. But now we require the reversal of power flow from converter 2 to converter 1. So now converter 2 acts as a rectifier and converter 1 acts as an inverter. So now at the converter 1 we requires what? Negative voltage, because that is act as an inverter. So to reduce the voltage or decrease the voltage, we require the ramp or exponential function that is followed by the current ramp to reach to the required level. So we can get the reversal power flow in the HVDC system. And this steps requires almost 20 to 30 milliseconds. So the basis of deciding the sequence followed, that is normally the ability of the AC system to survive the resulting disturbance and the need of the reversal of power flow within the specified time. So typically the fast power reversal time will be on the order of 20 to 30 millisecond. That is depends on the AC system limitations, DC cable design constraints, power dispatch conditions, and that may increase the several seconds. So HVDC control can meet this entire range of requirements. So this time requirement for the reversal of the power flow, that is depend upon the different conditions like AC system limitations, DC cable design constraints, and power dispatch condition. So you have to follow these two rules or two steps for the reversal of the power flow in the HVDC system. So this is nothing but starting, stopping, and power flow reversal in the HVDC system. So here I complete this topic. Next topic is the harmonics and filters. So we already discussed the different component of the HVDC system. We require the filters at the AC sides as well as we require the DC reactor at the DC side to remove the harmonics at both the AC and DC sides. So first we understand that what is the reason of generating the harmonics at the AC sides. So as we know that harmonics are generated because of the operating conditions of the system. Suppose that the overlap angle is increases, it means nu is increases, the harmonic component is decreases. So with the reductions, that being is more pronounced at the high harmonic. So with the higher level of commutation angle, the harmonic component, the AC side, that is decreases. So depending upon the operating condition of the HVDC system, the different types of harmonics are presented. Suppose it is a 6 pulse converter. So as we know that the dominant harmonic is a 5th and 7th harmonics. Same way, suppose it is a 12 pulse converter. So dominant harmonic is 11th and 13th order harmonics. So depending upon the operating condition and the system we have used in the HVDC system, we require the filters like high pass filter or tune filter. So you can see here in the figure, suppose it is a 12 pulse converter we require in the bipole HVDC system. So dominant harmonic in the bipole HVDC system is 11th and 13th order harmonic because we use the 12 pulse converters. So to remove this 12 pulse to remove this 11th and 13th dominant harmonics, we require the tune filter. It means we require the filter which is specially designed for 11th and 13th order harmonic. So you can see here this is series RLC, series RL, sorry, series LC. that is a tuned filter specifically designed for the 11th and 13th order harmonics. So it means that for 11th and 13th order frequency, this filter provides the low impedance. So whatever harmonics 11th and 30 at the AC side, that easily grounded through this path. You can see that here it is grounded. So that provide the low impedance for the 11th and 13th order harmonics. For the remaining harmonics, like other higher order harmonics, to remove it, we require the high pass filter. So for higher order harmonics, this high pass filter that provides the low impedance path and ground it effectively so that we can remove the higher order harmonics. So this is about the AC harmonic or AC filter to remove the harmonic at the AC sides. So now question is that why we require to remove this harmonic on the AC side? So the harmonics have to filter out sufficiently at the terminal, otherwise what will happen, that distort the AC system. You can see that here the harmonics have to be filtered out sufficiently at the terminal so that the harmonic enter into the AC systems are small and distortion of the AC voltage caused by the harmonic current is within the limit. Otherwise, that distort the voltage. So harmonic, if is not reduced by the filter, that creates the undesirable effect like a telephonic interference, higher losses and heating of the AC equipment. Or sometimes they create the resonance problem. So which could be create the over voltage or over current on the AC side. So to prevent this, we require the AC filter at the AC sides to remove all these harmonics. So another use of this AC filter is that to provide the sufficient amount of the reactive power. That we already discussed that each converter station that requires the 50% of the reactive power for the compensation. So out of this 50% reactive power requirement, 30% reactive power that is provided by this filter. 30% provided by among all these filter like this 11 and 13 tune filter as well as this high pass filter. So combine all this AC filter that provide the 30% of the total 50% requirement of the reactive power at the converter side. So that is another use of the AC filter at the AC side. So AC filter has two purposes. One is to provide the sufficient reactive power and second is to avoid any abnormal condition due to this harmonics like over voltage or over current. Same way at the DC side, harmonics we require the DC smooth reactor to remove this DC harmonics. So if it is a 12 pulse converter, we know that it is a harmonic order is 6, 12, 18, 24 like this way. Clear? If it is a 12 pulse converter, then order is multiple of 12 like 12, 24, 36 like this way. So to remove these harmonics, we require the reactor at the DC sides. So here I give this topic for the self-study. You have read this from the book Prabha Kundur. Page number 527. From this page, the detailed description of the DC side harmonics and how to remove this DC harmonics using the reactor, that is explained very well. We have already discussed, but you have to read this topic again. So detailed description is given in this page 527 from Prabha Kundur, which I have already provided to you. So this topic is over. Now next topic is influence of AC system strength on AC and DC system interactions. So here in HVDC system, you know that our normal AC system that is interacted with the high voltage DC system. So here we want to know that what is the impact of AC system strength on this AC-DC system interaction in the HVDC system. So first parameter which we identify, which decides that what is the strength of the AC system. So that first parameter is the short circuit ratio. So this short circuit ratio parameters gives the measure of the AC system strength. In short, from the short circuit ratio, we can decide what is the strength of AC system, like it is high, moderate or low. So what is the short circuit ratio? So short circuit ratio is nothing but a ratio of short circuit MVA of AC system divided by DC converter megawatt rating. DC converter megawatt rating is nothing but the megawatt rating power flow in the DC line. So how much megawatt DC line you have designed, HVDC line, that megawatt rating is the denominator, and short circuit MVA of the AC system, that is the numerator. So the ratio between these two, that is give the short circuit ratio. So in this definition, the short circuit MVA of the AC system that you get from this equation, short circuit MVA, that is equal to EAC square divided by ZTH. So here EAC, that is nothing but commutation bus voltage at the rated DC power, and ZTH, that is nothing but Thevenin's equivalent impedance of the AC system. And DC converter megawatt rating, that you already know, because once you design the HVDC system, your megawatt power transfer is fixed. Based on that, you have designed the HVDC system. So after that, you find out this short circuit ratio and check what is the strength of the AC system. So based on that, there are three categories, like it is also called as effective short circuit ratio. So basic SCR, basic short circuit ratio, that gives the inherent strength of the AC system. So from the viewpoint of HVDC system performance, it is more meaningful to consider the effective short circuit ratio. So what is the effective short circuit ratio? So in this we include the effect of AC side equipments, which is associated with the DC link, filter, shunt capacitor, and synchronous condenser. So now we consider the effective short circuit ratio by considering the effect of all this equipment. So now HVDC control, that plays a very important role in the most of the AC-DC system interaction phenomena, and that must be taken into consideration when assessing the acceptable level of system strength, AC system strength. So traditionally, the AC system strength has been classified into three categories based on the effective short circuit ratio. So first is the high. If the effective short circuit ratio is greater than 5. It is moderate if effective short circuit ratio is between 3 to 5, and low if it is less than 3. But after that, refinement in the DC and AC system control, the new development in the technology of the HVDC system control, now the classification is changed, and the high AC system strength we called if the effective short circuit ratio is greater than 3. It is low if it is between 2 to 3, and is very low if it is less than 2. So based on the effective short circuit ratio, we can say that the AC system strength is good or not, or high or low, because that directly impact the AC-DC system interactions, and that directly affect the HVDC system operation. Second parameter that influence the AC system strength, that affect the AC system strength, that is the reactive power requirement. So as you know that the converter consumes the reactive power, which increases with the increased power on the DC line. So with normally the accepted rectifier ignition angle delay alpha and inverter extinction angle gamma between 15 to 80 degree and commutating reactance exceed 15%, at that level the converter consumes a 50 to 60% reactive power in normal conditions. So generally this reactive power is provided by the converter side to prevent the large reactive power flow through the AC lines. So out of this 50 to 60% of the reactive power, part of the reactive power is provided by the capacitors or associated with the AC filter banks. So the least expensive way to provide the required reactive power is to use the shunt capacitor bank. So since the reactive power varies with the DC power transmitted, the capacitor must be provided in the appropriate size of switchable banks. So here you not provide the fixed capacitor because the reactive power requirement is vary. So to maintain the voltage within the range of plus or minus 5% at all the loads levels at the AC side, you require the dynamic reactive power support. So for that you require the appropriate size of switchable capacitor banks. So this will also influence the strength of the AC system. So if your system is stronger the AC system, the larger the switchable size bank is required to maintain the acceptable voltage between the plus or minus 5% at all the levels. So to make the AC system strength, you require the switchable size bank. If your AC system is stronger. If your system is not stronger, for the weak AC system, that requires the flex devices for the reactive power compensation. So here you can see that for the weak AC system, it may be necessary to provide the reactive compensation in the form of static VAR compensator. So static VAR compensator is nothing but a one type of flex devices that we will study in the next chapter. So for the weak AC system, we require the flex devices or the synchronous condenser for the reactive power compensation. Or maybe suppose generators are near to the DC terminal, then it is very helpful to provide the reactive power demands and maintaining the steady voltage within the range. But as we know that the generator is not near to the HVDC system. That's why we require the huge power transfer over a long distance through the HVDC system. So generally the generator are not near to the HVDC line. So that is not helpful to providing the sufficient amount of the reactive power. So generally we have required the flex devices if your system is weak. If your system is stronger, then we require the large switchable capacitor bank. So that maintain the acceptable voltage within the limit. So the reactive power requirement is also affect the AC system and DC system interaction. So here these two parameters which affect the AC-DC system interaction. One is the ESCR parameter from which you can identify the system strength, and another is the reactive power requirements. So if your reactive power requirement is very high for the stronger system, then you can use the switchable size capacitor bank, or if your system is weak, then you can go for the flex devices. Now next topic is what is the problem associated with the low effective short circuit ratio of the system. So there are basically 4 different problems associated with the operation of the DC system when it is connected with the weak AC system. Weak AC system means low effective short circuit ratio. So first problem happens because of low effective short circuit ratio, that is high dynamic overvoltage. So high dynamic overvoltage happens in the weak AC system. So let's understand this. When there is an interruption on the DC power transfer, the reactive power absorption of the HVDC converter drops to 0. This is obviously because when the HVDC power transfer is interrupted, it means there is no load. So what happens? The converter does not require any reactive power because converter is off at that time. So absorption of the reactive power at the HVDC converter, it drops to 0. Clear? So with the low effective short circuit ratio system, the result is what? Increase in the alternating voltage, because the reactive power requirement is reduces because converter is off. So at the converter side, we have excess amount of reactive power. So when excess amount of reactive power is happen, what will happen? The voltage is increases. So this sentence is, that's why I've written here, the resulting increase in the alternating voltage due to the shunt capacitors and the harmonic filter, because both are providing the reactive power. But now we not require the reactive power because there is an interruption of the DC power. So this will require the high insulation level of the terminal equipment. Why? Because voltage level is increased drastically, so that the terminal equipment that require the high insulation level to absorb this high voltage. So that creates a problem like may they damage the local customer equipment or the insulation at the AC side. So for voltage instability. So the DC system which is connected to the weak AC system, particularly on the inverter side, the alternating as well as direct voltage, that is very sensitive to the change in the loading. So when suddenly load change, suppose suddenly increase in the load, the direct current in the DC side will increase, that will fall the alternating voltage on the AC side. So consequently, the actual increase in the power, that is very small or negligible, but the control of the voltage and the recovery from the disturbance becomes very difficult, because now the voltage is reduces drastically to the very low value. So the DC system response may even contribute to the collapse of the AC system because the sensitivity increases with the large amount of the capacitors, shunt capacitors. So in such cases, in such system, the DC system control may contribute to the voltage instability by responding to the reduction in the alternating voltage. So how that contribute? So first is the power control increases the direct current to restore the power. So power control signal when given by the controller, so that will increase the direct current and to maintain the rated power. But at that time, what will happen? The alternating voltage at the AC side will reduces. So that will create the voltage instability at the AC side. Second way, the inverter gamma may be increased to maintain the volt commutation margin. So that is also increase the voltage instability. Third is the inverter draws the more reactive power with reduced voltage. Shunt capacitors, however, produce fewer reactive powers. So AC side voltage is low, so obviously the inverter draws the more reactive power to maintain the voltage at the inverter side at the rated value. But with the reduced voltage, shunt capacitor is not sufficient to provide the required amount of the reactive power. So at that time, what will happen? The voltage is collapsed and that creates the voltage instability. And another is that this alternating voltage is reduced and that creates the further aggravating situation. It means that creates the very dangerous situations. So this voltage instability that is created because of this DC system control when it is connected with the weak AC system. Clear? If your AC system is strong, then there is no problem. But when your AC system is weak, at that time your DC system control action that creates this type of problem. So first problem is high dynamic over voltage. Second problem is this voltage stability. And another is the harmonic resonance. So harmonic resonance is also created because at the AC side filter is provided. So by the DC control, the resonance happens between the two filters. So that is another problem created by the DC system. Fourth one is the voltage flicker. So this is another characteristic of the weak AC system, that is the switching of shunt capacitor and reactor that creates the unacceptable large voltage change in the vicinity of compensation equipment. So the transient voltage flicker because of frequently switching of the reactive devices like capacitor and reactor. So that creates the higher voltage on the DC sides as well as on the AC sides. Clear? So this creates the problem to the terminal equipments at the AC sides. So these are the problems created by the DC system when it is connected to the weak AC system. Now next topic is what is the solution of the problem associated with this weak system. So whatever the problem, this high dynamic over voltage, voltage instability, harmonic resonance and voltage flickers. So how to solve these problems with the weak system. So that topic I give you the self-study. And second topic, the response to DC and AC system faults, that also I give to the self-study. So these two topics for the self-study. So that you also read from the Prabha Kundur book. This first topic, solution to the problem associated with the weak system, that is given the page number 531. And the second topic, response to the DC and AC system fault, that is given the page number 533 on the chapter number 10, response to DC and AC system faults. So let's summarize this lecture. So in this lecture, we first start the starting, stopping and power reversal. How to stop, how to start and how the reversal of the power flow is achieved in the HVDC system. So there are the different steps in all the three cases: starting, stopping and power flow reversal. So if you operate your HVDC system in the proper sequence, you can achieve this starting, stopping and power flow reversal. Second is that filter, that we already discussed, but again repeat this: harmonic and filters, that AC filters, why require the AC filters and how to remove this harmonic at the AC sides. So that is we have discussed in this lecture. Then DC filter or DC harmonics, how to remove. So that is by using DC reactors, and how to design the reactors, and what is the value of reactor is required when you design the DC reactor to remove the DC harmonics. So that you have read from this chapter number 10. So that topic is also self study. I give you all the page number 527, chapter number 10 from the Prabha Kundu. Then we start the next topic, influence of the AC system strength on AC DC system interaction. So to identify the strength of the AC system, we find out the one parameter which is called the short circuit ratio. So based on that, you decide the strength of the AC system, it is high, low or medium. Then after we say that what is the impact of reactive power on the AC system strength, reactive power requirement, how to provide the sufficient reactive power requirement in the weak AC system as well as strong AC system. Weak AC system we require fixed devices SVC, and strong AC system you need the switchable capacitor bank to maintain the acceptable voltage level. And another is that what are the problems associated with this low effective short circuit ratio system, or what is the problem associated with the weak AC system. So that is nothing but high dynamic over voltage, voltage instability, harmonic resonance and voltage flickers. Then how to remove this, or what is the solution of this problem. So that is I give you self study that you have read from this chapter 10 page number 531. Same way second topic, response to AC/DC system fault. So all these two topics are the theoretical topics, so that's why I give the for the self study. So I hope you clear this topics, and I hope there is no doubt in this lecture. If you are in doubt, you note down and we discuss during the doubt solving session. Thank you.